Now let's identify the skewness of a binomial distribution and the effect that it has on the standard deviation. So I'm going to consider 3 distributions here that have got the same number of trials. All of them have 20 trials. And then we can look at the shapes and see that some of them are symmetrical and some of them really aren't. Now here I'm tossing a coin 20 times and I'm letting P, the chance of success, be the probability that I get heads. So that's half. Now if we've got 50-50 chance of getting heads and getting tails, then we can see that if we graph the distribution here, where the number along this x-axis here is the number of heads that I might get, then we can see that the mean is to get 10 heads, and we've got an equal chance of getting more or less than 10. And so putting a dot here for the probability of any one thing happening and lining up the dots, obviously it's not really correct to join the dots together because this is discrete data, it's not continuous, but we can see the shape that we would get if we did join it together, and it makes a wave that's definitely got that symmetry about it. Now here we're tossing a die 20 times in both these examples, but we're letting P be the chance of getting a 6, and that's only 1/6, not very likely. Where here we're letting P be the chance of not getting a 6, which is of course 5/6. So here we can see that the data is all skewed over here to the left-hand side of the graph. And that's because we're thinking that if we're tossing a die 20 times and we're looking at how many 6s we get, we probably won't get many. The most common things that will happen is 3 or perhaps 1 or 4. And then as we look at the chance of getting 20 6s out of 20, well that's astronomically small. And in fact, it's so close to 0 all the way along here that it looks like there's really not much chance of getting any more than about 10 6s. Obviously there's some chance, it's not 0, but given my scale, it's really, really small. So again, we can't join the dots together because this is discrete data, but we can definitely see that we've got this wave here that's popping up right over to the left. Whereas this one has our wave popping right over to the right because of course the chance of not getting 6 is really good. So that's going to happen lots and lots of times, and so the data is all skewed over here. Now, this is something that people find hard to learn and remember for some reason. We call this being skewed to the right, even though the big chunk of data is on the left. And that's because the longer tail is on the right-hand side. So we need to remember it around that way. When we have the longer tail on the left-hand side of the graph, we say that it is skewed to the left. So that might seem the opposite way around from what you might expect. Something to learn there. Now, if we actually look at the mean here, the mean is understandably low for this one and high for this one, but the standard deviation of each of these is exactly the same. And you'll notice the standard deviation of these is a lot lower than the standard deviation of this one. And the reason for that is that the standard deviation is a measure of spread. How far away is each score from the mean? So if your mean is really close to one end or the other, then there's not much room for scores to be very far away on one side. And that means that you will have them generally more clustered. And that's because there's just nowhere for them to go at one end of the distribution or the other. So I've written here, if 2 distributions have the same number of trials, the standard deviation is smaller the more skewed the distribution. So a simple example here to test this idea, 2 binomial random variables x and y both consist of 100 Bernoulli trials. For x, p equals q, whereas for y, p is 1/10, so that means that q would be 9/10. Find the ratio of their standard deviations. Okay, so for x, let's say we'll call it standard deviation of x. It's going to be, now what's the formula? Square root of n times p times q, which is the square root of 100 times, now if p and q are both equal to each other and they both add to 1, they must both be half. So we've got half times a half. So a quarter of 100 is 25, and the square root of 25 is 5. Whereas for y, the standard deviation of y is going to again be np cubed in square root, but this is 100 times 1/10 times q, which is 9/10. So we get, what's that, 900 divided by 100, that's 9, and the square root of 9 is 3. So therefore, we can say that the standard deviation of x to the standard deviation of y is equal to 5 to 3.